Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In this episode, we'll discuss Richardson Extrapolation. Richardson Extrapolation is a method to improve our computed values for a numerical integration. So, for example, if we use trapezoidal rule, we have an error that is proportional to the subinterval size squared. Trapezoidal rule error is minus the second derivative somewhere on the interval over 12 times the length of the interval, b minus a, times the subinterval size squared. The Simpson's rule error was minus the fourth derivative somewhere on the interval divided by 180 times the length of the interval, b minus a, times the subinterval size to the fourth, where by the subinterval size we mean that Simpson's rule using 3 points, those 3 points are each separated by a length of h, and so the whole interval separating those 3 points is 2h. So suppose we've performed trapezoidal rule for several values of h. How can we use those values in order to get an improved value for the true integral, the true area under the curve? So if we know the form of the error term, as we do with trapezoidal and Simpson's rule, that the error term is proportional to h squared for trapezoidal rule, to h to the fourth for Simpson's rule, we can use that knowledge to improve our estimate of the integral's value. So let's see how we go about doing that. Well, the true value of the integral is our computed value plus some number times h to the p, where p, again, that's the order of our scheme. Again, the error, h squared for trapezoidal rule, h to the fourth for Simpson's rule. And then we compute, use that method, trapezoidal rule, say, with a subinterval size h over 2. We have the interval size, and we get another approximation for our integral, and there we have that the true value is the computed value that we get, say, with trapezoidal rule, plus some constant times now h over 2 to the p. Well, we have two equations over here, and we can eliminate, knowing p, find the true value, or a better approximation for the true value of the integral. How we do that is that we multiply the second equation times 2 to the p. So the first equation stays the same. The second equation is multiplied by 2 to the p. That enables us to just subtract, eliminating the ch to the p terms, and we get 2 to the p minus 1 times the new true value, the new updated true value, if you will, is approximately 2 to the p times the finer estimate, the estimate that we have for the integral on the finer mesh, minus 1 times the computed value on the coarser mesh. So we just divide by 2 to the p minus 1, and what we get is an updated approximation for the integral is equal to 2 to the p times our finer computed value minus 1 times our coarser computed value divided by 2 to the p minus 1. And notice that makes sense in that what we've done is we've taken 2 to the p minus 1 computed values divided by 2 to the p minus 1, so we get a weighted average of our previously computed values, and we're taking more of the finer value than the coarser value, which also makes sense. Let's work an example. The integral of 1 over 1 plus x from 0 to 1 is natural log of 2, which is 0.693, 14718, etc. And if we use just one trapezoid, we'd get an approximate integral of 0.75. If we take h as a half, we'll have two trapezoids giving us 0.7083333. If h is a quarter, we get a value. H is 1/8 and h is 1/16. And what we do is, since for trapezoidal rule p is 2, remember the error is order h squared, that's why we get the 2. So what we do is we take 4 times the finer computed integral minus the coarser divided by 2 squared minus 1, or 3. So what we would do is in this case, we would take 4 times 7083333 minus 1 times 0.75, and we divide by 3 to get an updated value, which is 0.694444. If we use h is 1/2 and 1/4, taking 4 of the fine value minus 1 of the coarse value, dividing by 3, we'll get 0.693254. And we can go on in that manner, and we can see that our updated values are quite a bit closer to the true value than the original value. Now, it turns out that for trapezoidal rule, the error can be written as c1 times h squared plus c2 times h to the fourth plus c3 times h to the sixth, etc. So once we've done one step of the trapezoidal rule, what we've done is we've eliminated the h squared portion. And now our new error is going to be something like h to the fourth. Well, if we have h to the fourth, how does that change the method? If p is 4, we have 2 to the fourth, or 16 times the finer value minus 1 times the coarser value over 16 minus 1, which is 15. So that's what we're doing with the second update. We're taking 16 times 0.693254 minus 1 times 0.694444 and dividing by 15 to get 0.693175. Similarly, if we take these two middle values, we take 16 times the finer one, 693,155, minus 1 times 0.693254, divide the result by 15, and you could see that we're almost exactly right in terms of the integral. Then we could go further. Once we've eliminated the square terms, the h to the fourth terms, then our error would be on the order of h to the sixth. And so what we would do is we'd take 2 to the sixth, or 64, times the fine value minus 1 times the coarse value over 64 minus 1, or 63. In other words, over here, we're taking 0.693148, 64 of those minus 0.693175, dividing the result by 63, and we get 0.693147. Now, suppose we didn't know the error order. Suppose we didn't know p, but we have the iterates that we get the computed values in our iteration scheme for a certain step size h, h over 2, h over 4. Well, we can use the same idea, but instead of solving for the true value of the integral, what we could do is we can solve for p, for what is the order of this scheme, doing for our particular integration problem. So again, we have the true value is approximately the computed value for a given step size, interval size, plus c times h to the p, where p is now not known. And we could do it again for having the subinterval size and then having the subinterval size again. And let me note that there's no rule that you have to always take half of the previous subinterval size. In the previous analysis, we could have taken 1/3 of the previous h value and worked it out in that manner. It's just very convenient to have the interval size in many cases. So what we have is these three equations for that are approximations for our true integral. We've computed three values, and we want to find how fast the convergence, what's the order, what's the error of the scheme. And so we can take these equations and eliminate I true, because we don't know that, and we could solve for p. So what we could do is we can subtract these equations, eliminating I true. And so, for example, if we take the second equation minus the first equation, then we'll get the top equation on the right. If we take the third equation minus the second equation and reorder the terms, we'll get this second equation on the right. So the top equation involves using grid size h and h over 2. And the second equation on the right uses the two finer computations, grid size h over 2 and h over 4. And if we divide these equations, we could see that we eliminate the c. And then in order to eliminate the denominators, if we multiply by 2 to the p times 2 to the p, we get some simplification that works out when we solve for p, and we work it through, and we can find that p which is, recall our error term is something like CH to the P is log base 2 of the computation using grid size H over 2 minus the most coarse grid size divided by the fine grid size minus the H over 2 grid size. So here, if we've computed 3 values of the integral, we can approximate the value of P. So going back to the same problem that we had before, the integral from 0 to 1 of 1 over 1 plus x. We had our approximations using trapezoidal rule. And if we take the first 3 values and plug it into this equation, what do we get? We get P is equal to log base 2, the middle value minus the coarse value, divided by the fine value minus the middle value. Okay, we take the log base 2 of that, and we get, it's about 1.88. If we take the second, third, and fourth values and do the same thing, we get another approximate value for P. If we take the 3 finest values here, we plug in up here, right, we get 1.99. And we know that the true value is 2, and we see that this is a way that one can approximate the value of P. Let's have a moment of culture. The USDA once wanted to make cows that produce milk faster to improve the dairy industry. So they decided to consult the foremost biologists and DNA technicians to help them build a better cow. So they assembled this team of great scientists and gave them tremendous amounts of funding. They requested rare chemicals, weird bacteria, tons of quarantine equipment. There was a horrible typhus epidemic that they started by accident. And 2 years later, they came back with the new improved cow. It had milk production of 2% greater than the original cows. So then they tried going to the greatest Nobel Prize winning chemists that they could find. They worked for 6 months and they requisitioned tons of chemical equipment. They poisoned half of the small town in Colorado where they were working. And their experiments were tremendously toxic, and they were able, after about 6 months, to get an improvement of 5% in milk production per cow. So they went to the physicists, and the physicists tried for a year. And after they irradiated 10,000 cows, they got about a 1% improvement in output. Finally, in desperation, they turned to the mathematicians. The foremost mathematician of his time offered to help them with the problem. And upon hearing the problem, he told the delegation that they should come back in the morning and he'd have the problem solved. In the morning they came back and he handed them a piece of paper with the computations for the new 300% improved milk cow. And his plan began: a proof of the attainability of increased milk output from bovines. Consider a spherical cow. I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.